Welcome back for day two. So, day two, what we're focusing on is I can perform normal distribution calculations and interpret their results. So basically, we're going to be doing the same thing we were doing yesterday, but putting context around the problems that we're looking at. So, here we are going to reintroduce this four-step process model, okay? Because eventually, again, every problem we do is going to become a four-step process. So let's get in that good habit right away. So state, we're going to express a problem in terms of the variable. Plan, we're going to draw the picture of the distribution and shade the part of interest. Do, we're going to perform calculations. We're going to determine the z-scores, and we're going to find out the area, and then conclude, we're just going to write our conclusion. So let's look at our first example. When Tiger Woods hits his driver, the distance the ball travels can be described by a normal distribution with a mean of 304 and a standard deviation of 8. What percent of Tiger's strides travel between 305 and 325 yards? So, what are we looking for? So state, we're just describing. Well, we're going to let x be the distance that his ball travels. And what we're looking for is the probability of one landing between 305 and 325, okay? Because that's going to be the percent, right? Probability percents are kind of equivalent ideas. So what we're really looking for is that probability of one landing between 305 and 325. So in the plan phase, remember, we're going to draw our picture, okay? And remember, to draw our picture, what we're looking for is putting the center, so 304, and then marking those standard deviation marks. 1, 2, and 3 standard deviations. This one, don't worry about being 4 standard deviations out, because that's virtually no area beyond those 3 markers. All right? So you always want to give me a quick sketch to show me what area that you're looking for. So from there, let's start doing some calculations. So the difference between yesterday and today is yesterday you were being given these z-scores. Today, you need to find the z-scores for me, okay? So we need to look at this and say, well, what is the z-score for getting 305 or getting 325? Well, remember, you take your observation minus the mean divided by, well, I forgot already what's the standard deviation. It was 8. So divided by 8. So 305 minus 304 is 1 divided by 8. So that has a z-score of 0.125. And then this one, your observation minus the mean divided by standard deviation. So 325 minus 304, whoops, 325 minus 304 is 21 divided by 8 has a z-score of 2.625. Okay, so here, what you need to do is always standardize your information, okay? Whenever you're looking for normal calculations, always standardize. So what started as a probability of x being between 305 and 325 is now turning into a probability of z having a z-score between 0.125 and 2.625. Okay? And once we have those z-scores, once I've noted it in z-score context, now we can do what we did yesterday. And remember, yesterday, that is what normal CDF does. Normal CDF takes z-scores and finds the probability of having areas between them. So here, having probability of going between 0.125 and 2.625. I can calculate the area between those two z-scores. and it's going to be 44.59%. Oh, I should do 0.4459. So what is our conclusion? Well, our conclusion is about 44% of tiger strides travel between 305 and 325 yards. So in your conclusion, you're always bringing it back to the context of the problem, okay? So always do your answers to actually answer the question, okay? Now, let's do another one. So, the average height of 17-year-old males can be described with a normal distribution with a mean of 70 and standard deviation of 3.1. What percent of 17-year-old males are taller than 75 inches? So to state our problem, if we let x be the height of a 17-year-old male, we want to know what's the probability that that male is going to be over 75 inches tall. Okay, remember percents, probabilities are basically interchangeable in this context. So that's what we're going to be looking for. Now, in order to do a plan for this, remember a plan is the picture, all right? So our plan is centered at 70, then 1, 2, 3, 1, 2, 3. So here would be 73.1, 76.2. So to be above 75 inches, we're looking at somewhere like this. All right, so plan by making your sketch. And now the do is actually doing that calculation. So whenever we're finding a normal probability, we need the z-score, okay? So the z-score here is for an observation of 75 with a mean of 70, standard deviation of 3.1. So 5 divided by 3.1 is about 1.61. Okay, so now we started with a probability of having x, the height, being greater than 75, has now become a problem of probability of having a z-score above 1.61, approximately. Okay, again, there's some rounding in there. And now whenever we have a z-score and we're looking for the area, we're looking for the probability, that is going to be normal CDF. This time our lower bound is that 1.61. Upper, well, it's going up to infinity. It's going up forever, so we just need a large value, okay? Since our calculator can't recognize infinity. And then we're using standardized values. So that probability is going to be about 0.0537. Or putting that back in context, there's about a 5% chance of 17-year-old males are taller than 75 inches. All right, so let's keep this going. How tall is a 17-year-old male who is at the 20th percentile for height? Okay, so X is once again going to represent a 17-year-old, the height of a 17-year-old male, but this time we're being given opposite information. Okay, this time we have that same distribution. 1, 2, 3, 1, 2, 3 standard deviations. And we want to know what is the height at the 70th percentile, or sorry, 20th percentile. So that's going to be somewhere in here. So remember, if we have the area, okay, now our goal is to reverse engineer the z-score, okay? To reverse engineer the z-score, remember, that's an opposite command. If I have the percent and I'm going to z-score, remember, that's the inverse norm command, because that's what's prompting you, hey, you know the area. Oh, let's figure out the z-score from that area. Okay, so again, we're reverse engineering that z-score. So the z-score is going to be negative 0.84. Okay, so that's the z-score that creates the 20th percentile. Okay, the z-score that marks a point that 20% of the data is less than it. But that's still not the height, right? So this time we have to go a little bit deeper, okay? So remember our formula. Right? So now, this time, we know the z-score is negative 0.84. We don't know the observation, but we know the mean is 70 with a standard deviation of 3.1. So using that formula, we can still go in between the z-score and the actual data point, right? It works interchangeably in either direction. If I know the z-score, I can find the observation. If I know the observation, I can find the z-score. So now this is just some basic algebra skills. So I'm going to take that negative 0.84, multiply it by the 3.1. So I'm going to have negative 2.604 equals x minus 70, and then I'm going to add 70 to that. So I'm going to get a height of 67.396. And what is that telling me? So I'm a 17-year-old male who is about 67.4 inches tall is at the 20th percentile. This means about 20% of 17-year-old males are shorter than 67.4 inches. Okay, so to thoroughly describe what we just found, that tells us, okay, 20th percentile is at what point is 20% of the data less than the observation you're talking about. And in this case, we calculated that to be the 67.4 inches. Okay, so, and I believe that is all for our notes today. So, thank you so much for joining me. And again, please make sure you ask if you have any questions about how to do these calculations.